Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. In the Module 6, we are now studying about aldehydes and ketones. In the first lecture, we will be studying about preparation and the properties of aldehydes and ketones. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. So the various topics that will be covered in this particular session include preparations of aldehydes and ketones. We will be studying about various oxidation methods. We will also be studying about various reduction methods of synthesis of aldehydes and ketones. Ozonalysis reaction also we will be studying, and how Grignard reaction can be used to prepare aldehydes and ketones we can also study. And we will also be studying about Friedel-Crafts reactions, mainly Friedel-Crafts acylation for the preparation of ketones. So these are all the various topics that we will be studying in this particular session.
Ketones and aldehydes. Structure of ketones and aldehydes. For the carbonyl compounds, C double bond O is the functional group for ketones and aldehydes. When R is a hydrogen, it is an aldehyde. When R, both the R's are alkyl groups, they are ketones. Here also, the carbonyl carbon is sp2 hybridized. In the case of alcohols, the oxygen is sp2 hybridized. In the case of ketones and aldehydes, the carbonyl carbon is sp2 hybridized. Let us go to the physical properties. Aldehydes and ketones have higher boiling point than hydrocarbons, but they have lower boiling point than alcohols. In the case of alcohols, there is hydrogen bonding, so their boiling points are higher. Whereas in the case of ketones and aldehydes, there is no hydrogen bonding or less hydrogen bonding, due to which we have lower boiling point. Acetone and acetaldehyde are the two lower ketone and aldehydes which are miscible with water, that is soluble. But when the alkyl group size increases, the solubility decreases. Synthesis of aldehydes and ketones. There are different methods available for the synthesis of aldehydes and ketone. One is oxidation of alcohols. Another one is ozonalysis of alkenes. Oxidation. A simple alkane can be oxidized to an alcohol, which on further oxidation gives an aldehyde, which on further oxidation gives a carboxylic acid. The next one is pyridinium chlorochromate. The PCC is a much milder oxidizing agent than the previously seen potassium dichromate. So this oxidizes primary alcohols to aldehyde and the secondary alcohols to ketone. So oxidation of primary alcohols. When we use chromium trioxide in pyridine, that is pyridinium chlorochromate, we oxidize primary alcohols into aldehydes. The heptanol is oxidized to heptanal, and the yields of these reactions are quite high. Swan oxidation is a combination of DMSO in oxalyl chloride, which is a very mild oxidizing agent. If you look at the temperature, the reaction is run at minus 60 degrees centigrade. So that means it is a very, very milder oxidizing agent. And if we look at oxidation summary, the same starting material, the substituted primary alcohol can be oxidized to a carboxylic acid with the help of stronger oxidizing agent, that is sodium dichromate, a mild to an aldehyde with the help of PCC, again the same aldehyde with the help of Swern oxidation, that is oxalyl chloride. So the same starting material, the primary alcohol, can be converted to either carboxylic acid or aldehyde using different reagents. Ozonolysis is the next reaction we can see. Aldehydes and ketones can be produced by the breakage of double bond. The ozonolysis of this double bond leads to two carbonyl compounds. And if it is a cyclic one, we end up with one compound having two carbonyl units. From nitriles. So nitriles can be converted to ketone or aldehyde by diol H reduction. That means nitriles give aldehydes on diol H reduction, and Grignard reagents when reacted with nitriles gives ketone. So these are all the two different methods by which nitriles or the cyanides can be converted to ketone or aldehydes.
Let us now look at the synthesis of aldehydes. So we will now look at various synthetic methods by which aldehydes can be synthesized. The first one is a partial oxidation of primary alcohols, then reduction of acid derivatives, ozonolysis of alkenes, mainly RCH double bond CHR1 R prime type alkenes, where there should be at least one proton on the alkene carbon. Then oxidation of vicinal diols. Aldehydes can also be synthesized from alkynes, and we will also study about Stephen's method. Then an industrially important process called the Oxo process or the hydroformylation reaction and the Grignard reaction. These are all some of the methods by which aldehydes can be synthesized. We will be looking at one by one. So the first one is the primary alcohol oxidation. So primary alcohol, when treated with pyridinium chlorochromate, can form aldehyde. This is a very mild conditions. There is also another important method based on DMSO, dimethyl sulfoxide based oxidation. This is a very versatile method for preparation of aldehydes from primary alcohols. So the primary alcohol can be treated with dicyclohexyl carbodiamide DCC to produce the corresponding urea derivative, and this one can be treated with the dimethyl sulfoxide to form the aldehyde in the presence of a base. We will just now, after completion of a few other methods, we will look at the mechanism for this particular reaction. So the second one is the alcohols can be treated with trifluoroacetic anhydride to give the corresponding trifluoroacetate salt, and which can be treated with the DMSO in the presence of a base to produce primary aldehydes. Primary alcohol can also be treated with sulfonyl chlorides, alkyl sulfonyl chlorides, to form the corresponding sulfonate ester, and this sulfonate ester on treatment with the DMSO and base gives aldehydes. Or primary alcohol can also be converted to the corresponding halo derivatives, especially in this particular case the bromo derivative with the help of PBr3, and the corresponding alkyl bromide can be treated with dimethyl sulfoxide and base to give the corresponding aldehydes. So these are all the various methods by which the alcohol can be converted to the corresponding aldehydes. So these are all the oxo derivatives. If you look here, this one or the trifluoroacetate or the sulfonate esters, these are all the esters of oxygen. So these are oxygen derivatives, and these derivatives can be converted to this aldehyde by treatment with dimethyl sulfoxide. Let us look at the mechanism by which the reaction, how it proceeds. So this is basically like a SN2 type mechanism. So the dimethyl sulfoxide is polarized towards the oxygen because oxygen is more electronegative than the sulfur. So the sulfur is having delta positive charge, or positive charge remains on the sulfur, and oxygen is having the negative charge. So this nucleophilic oxygen can attack this particular carbon and X is the leaving group. So the rear side attack of this particular nucleophile happens on this particular alkyl halide. So basically here it is not an alkyl halide, here it is a leaving group, the one which we had seen, the sulfonate or the trifluoroacetate esters of the corresponding alcohol is the one which is given. So X here is a leaving group. And after the SN2 type attack, we get this alkoxyl sulfonium salt is formed, and halide is, or it is not the halide, it is the leaving group is lost as a anion. So this entire unit is actually from the dimethyl sulfoxide moiety, and the leaving group is actually lost. So this part RCH2 is the one which is present here, and this X is nothing but the leaving group which is lost here as shown. Now this intermediate is attacked by the base. So the base abstracts this particular proton, which leads to this particular sulfur ylide. Here we have a plus charge and we have a minus charge, so this type of compounds are called ylides, and this is based on sulfur, so this is a sulfur ylide. So the base abstracts the proton and it forms a anion on this particular carbon. So this anion now abstracts a proton from the internally from the CH2 unit from this molecule, this part of the molecule, and when this abstracts a proton, this bonded electrons are now shifted to the carbon oxygen bond, and once this happens, now the oxygen becomes more, this particular SO bond is broken because the sulfur is having a plus charge, so this is actually shifted to the sulfur, and this is how the electron movement happens. And when this type of electron movement happens, what we end up with is a dimethyl sulfide. This particular bond, the electrons between this CH bond is shifted between carbon and oxygen, so that is how we get the C double bond O here. So this is how the whole reaction proceeds, and the X here is the leaving group. The previous one we had seen what is the leaving groups. They may be sulfonyl chloride salts of the sulfonate esters or trifluoroacetate esters, or even the halide, the last one. So these are all the various leaving groups, and in this particular case hydroxide ion is a very poor leaving group, so that is converted to a better leaving group by treatment with either trifluoroacetic anhydride or sulfonyl chlorides. So the next one is reduction of acid derivatives. So in the reduction of acid derivatives, we have Rochamond reduction. In this particular case, the carboxylic acid is converted to the acid chloride by treatment with the thionyl chloride, and this acid chloride is reduced with palladized barium sulfate is a negative catalyst used in this particular reaction. The palladium's activity is reduced by the addition of barium sulfate. So in this particular reduction, the acid chloride is converted into the corresponding aldehyde. The next one is the metal hydride reduction. The cyanides or nitriles were treated with lithium aluminium hydride in the presence of ether. Ether is used as a solvent, and an acidic workup finally produces the corresponding aldehyde. So cyanide can be converted to aldehyde with the help of lithium aluminium hydride. So this reaction is basically carried out using an inverse addition. That is, what is inverse addition is, generally the lithium aluminium hydride is added to the nitrile. That means the reagent is added to the substrate and not the substrates added to the reagent. So that is why this is called the inverse addition reaction. So why we have to do the inverse addition is, if the nitrile is added to the lithium aluminum hydride, then what happens is a reduction of the nitrile group directly takes place to give the amine, and our corresponding aldehyde cannot be prepared by this method. So we have to follow inverse addition in this particular case. Then the next one is reduction of acid chloride using diball H. The previous one we had seen Rochambeau reduction, so this is an alternative to Rochambeau reduction. In this particular case, acid chloride can be reduced using diball H. So the acid chloride is treated with the diball H at minus 80 degrees centigrade. That is, this reaction is always carried out at very low temperatures, and the corresponding aldehyde is produced. Similarly, esters and nitriles can also be reduced using diball H, as shown here. Here again the reaction conditions are very low temperatures. Minus 78 degrees centigrade is the temperature at which these type of reactions are carried out, and reduction of either ester or nitrile produces the corresponding aldehydes. And here is the structure of diball H, that is, this is the isobutyl unit. So two isobutyl units are present in the central atom is aluminium. So this is diisobutyl aluminium and the hydride is present. So this is the reducing agent which is used in these kind of reactions. And the next one is ozonolysis of alkenes. Mainly the alkene should have RCH double bond. That means one hydrogen should be present in the alkene carbon. Then only this reduction, this ozonolysis will produce the corresponding aldehyde. So alkenes of this type treated with ozone and zinc and water produces the corresponding aldehydes. Then the next one is the oxidation of vicinal diols. So the diol can be oxidized with lead tetraacetate or sodium periodate to produce two different alcohols. Basically this CC bond, the vicinal diols bond, is broken to produce a corresponding this part RCHO. This is one aldehyde, and this is the other aldehyde R prime CHO. So these two aldehydes are produced by the cleavage of vicinal diols. And in the case of sodium periodate, the intermediate formed is shown here. The iodate minus ion reacts with the diols to produce the hypervalent iodine species, and this undergoes cleavage to produce the corresponding aldehydes. And the next one is from alkynes. Mercuration and demercuration reaction is one reaction in which an alkyne can be converted to corresponding aldehyde. So here acetylene is taken as an example, and mercuric sulfate reacts with alkene, that is acetylene, and an acidic workup produces a corresponding acetaldehyde. Similarly, hydroboration reaction can also be employed on an alkyne. So this alkyne is treated with diborane, and hydrogen peroxide based oxidative cleavage finally in the presence of a base produces the corresponding aldehydes. So these are all the two different methods by which an alkyne or a triple bond compound can be converted to aldehydes. So the next one is a Stephen's method. In this particular case, a cyanide or the nitrile is treated with stannous chloride in the presence of hydrochloric acid and water, gives the corresponding aldehyde. So this is another reduction method. This is a Lewis acid generally used in this particular reaction. And another important process is a oxo process. Also, it's an industrial process. Here an alkene is treated with water gas, that is carbon monoxide and hydrogen. A mixture of these two gases is called the water gas, and this is treated with alkene in the presence of a transition metal catalyst. Basically here the cobalt carbonyl is used, and at a high temperature 170 degrees centigrade and a very high atmospheric pressure, that is under pressure. This is an industrial process, so the temperature and the pressure are very high for this particular reaction. This produces two types of aldehydes. The formyl group, that is the CHO group, is added to the terminal alkene as shown here. So we end up with a linear aldehyde, and if the formyl group is added to the internal carbon, then we end up with a branched aldehyde. So these two products are formed in this particular reaction. Since formyl group, that is the CHO, is added to the substrate, this reaction is also called hydroformylation reaction. This is a very, very important industrial preparation method for aldehydes. And the next one is a Grignard reaction. So in a Grignard reaction, we can use a formyl esters. A formyl ester is treated with a methyl magnesium or any other alkyl magnesium halide, and final acidic workup produces the corresponding aldehydes. The aldehyde R group generally comes from the alkyl magnesium halide. So this reaction, since aldehyde can also undergo further Grignard reaction, this is a very tricky condition to control. The major problem is if more of this aldehyde is formed and if more of this particular alkyl magnesium halide is present, then these two can further undergo reaction to give our secondary alcohols. To stop the reaction from moving forward, what we need to do is we have to very carefully control the quantities of the substrates and the reagent that are being used. So to avoid additional reaction between the alkyl magnesium halide and the aldehyde, the formyl ester is generally used in large excess. So if you use large excess of this one and a small amount of this alkyl magnesium halide, then all the magnesium halide is converted to this corresponding aldehyde and the reaction stops. So that way we can actually selectively make the aldehyde using this particular method. The next one is use of hydrogen cyanide. So when hydrogen cyanide is treated with alkyl magnesium halide followed by acidic workup, produces aldehyde. So this is also another method based on Grignard reaction.
Then the famous Friedel-Crafts reaction. We can also prepare ketones from acids, nitriles and esters. We will look at all these different types of reactions one by one. An alkane can also be oxidized to a secondary alcohol. The oxidation of secondary alcohol gives ketone. So these are all the different types of oxidation methods by which aldehydes and ketones can be produced. Oxidation of secondary alcohols with chromium 6. So in this case, a secondary alcohol is oxidized to a ketone. And if we take cyclohexanol, cyclohexanol is oxidized to cyclohexanone. So the secondary alcohol is oxidized to a ketone. Sodium hypochlorite is another oxidizing agent which can also oxidize cyclohexanol to cyclohexanone. This is commonly used as a household bleach. And this compound is a better option for acid sensitive compounds. The next one is the famous Friedel-Crafts reaction. George Wohler received his Nobel Prize for his contributions to carbocation chemistry, and he was the first one to work mainly on Friedel-Crafts reaction. And what is a Friedel-Crafts acylation reaction? So acylation of aromatic rings using an acid chloride or acid anhydride in the presence of a Lewis acid, mainly AlCl3, is called a Friedel-Crafts acylation reaction. Ketones from acids. A carboxylic acid, when treated with lithium hydroxide, gives the lithium salt, which when treated with alkyl lithium reagents gives the dilithio derivative, which on hydrolysis gives ketones. So this is an indirect method of making ketones from a carboxylic acid.
So in the case of synthesis of ketones, we have an oxidation method. Secondary alcohol can be oxidized as we have seen recently. The various oxidizing agents which we can use include acidic solutions of chromate and dichromate, or acidic permanganate can also be used for the oxidation of secondary alcohols to ketone. And there is another milder method where manganese dioxide or MnO2 can be used to in another method, manganese dioxide or MnO2 can be used to oxidize allylic alcohols. So in this particular case, it's a very selective oxidation. We get the corresponding alpha beta unsaturated carbonyl compound. Ozonalysis of alkenes also is possible where R2C double bond C R prime 2 type alkenes can be ozonalized to produce the corresponding ketones. So here both are alkyl groups. This also is an alkyl group. We can have 4 different alkyl groups are also possible. This alkene on ozonalysis followed by treatment with the zinc and water produces the corresponding carbonyl compounds. Then another method is oxidative cleavage of alkenes with Lumix reagent. So Lumix reagent is nothing but sodium periodate and KMnO4. In this particular case, KMnO4 is used as in very small amount or catalytic quantities. So the KMnO4 generally dihydroxylates the alkene, and this is followed by treatment with the IO4 minus produces the corresponding ketones. So the step 1 is the formation of cis diol. So in this particular case, we end up with a cis diol. That is the first step, followed by the formation of the ketone. In the second step, this is cleaved to produce the corresponding ketone. In summary, let us recap what we have studied so far. We have studied various methods for the preparation of aldehydes and ketone. We have studied various oxidation methods, basically DMSO, dimethyl sulfoxide based methods we have studied. We have also studied about Swan oxidation. We have studied various reduction methods, that is reduction of acid chlorides, esters, nitrile to give aldehydes or ketones. We also have studied about ozonalysis method for the preparation of aldehydes and ketones. In the case of Grignard reactions, we studied how nitriles can be converted into aldehydes. And in the case of Friedel-Crafts acylation reactions, how ketones can be synthesized from the aromatic units. That's what we have studied in this particular session. With this, we conclude the preparation of aldehydes and ketones. Thank you.